propane should fit. Maybe it's massive.
Have you ever seen it on TV?
No, they don't see no film. See, it's like
Last we all do.
no. And some of them, I think that's in that.
Here.
Or sometimes
Here's what?
it's hard to read. Oh, that's something about smart nipples. That's what I always carry my own because walking in country, you know what's in terms of
We've got to move to a different class. 108 is not going to get with it for that classroom. But 108 industry training.
oh yeah.
Start on our option. So it's still up here.
Training college, your practice what you might want. I was gonna change my car.
Let's go to France and get left.
Two?
Hey Mason, did you understand the print assignment?
Yeah.
Did you?
Yeah.
I like this.
That's more than any of the others. Yeah, I had John Wayne.
Arthur was in pretty much the whole book.
Except for when he died and then he wasn't in the last part, so I just kind of skimmed it.
I just skimmed over for Arthur's name and then I was like, oh fuck, gotta write something down.
Yeah. I don't know if you had these. I don't think they have a typo. They have the smallest magnitude in less than 0. You have to do 63. Oh, I picked 9, 60. Those are the last three. Do we ever do anything like that? Those are the definitions. When it's added unity and when it's always and I'll implement it. So I implement it, why do I want it? And then I add it. That's like the definition of page 940. 40 definitions. We'll do one. Our plan is only one for one. We have that. Man off on the can, then we shut it and turn on the fan because it's hot. Yeah. It's for the I'll wrap up, yeah.
Actually, warmer in the hall today.
I don't.
I did. So,
Do you?
well, it's online, so I printed it off and just did it.
Oh, I don't actually know if I'm right.
Please, you have, here's your text.
I saw that that's what I did, so I don't know how to do this.
Dale, you haven't given out that third part yet, have you?
I was gonna do that today.
Okay.
If you want, go ahead and hand it out now if you want, that's fine. I'm gonna do the same.
Okay, I got close.
I got the same thing.
Yeah, like.
So, solve it.
That's
the one that I'm having trouble with.
I did it over like I took
FFX was actually just 2
organized
so
stuff
then we
and
did
then stuff, and I
F
plugged
2
it
minus
into
delta
that to
1
get
equals the minimum distance, and so then I did that and I just solved the best.
So like the F(3) minus delta, that would equal the negative, would equal the smaller one out of these since it's
Yeah, no, like, I just did like the same steps.
Straight lecture
I'm the one that had sign of it.
most of it.
But you have to do
And
that
whenever
with
like he
the
goes
F(3)
off
minus
camera, I
delta.
think one of us is doing
You'll get 2 answers.
I can hear him good enough to understand what to write. Whereas a lot of people are just like,
Also, hand it out, trying to fill the forward, I never got it up.
So for 43, you
Oh.
just.
Because it was still section 2, so I did 2 minus M1 or whatever. I just took the answer because I still couldn't get both.
Wait, 43 or?
3.
I know, but that one doesn't have sign. 47.
Oh yeah, I
has
was just sign. I was confused.
Oh my
Sign. 47. I was supposed to be sign. Blah, blah, blah.
Yeah.
Okay.
I didn't mess with that because then you can take the inverse sign on both sides and get rid of your sign. So I did that and I took the inverse sign on both sides and it's like 5/4 and 7/4. Or
This is what
this
we
one.
did today.
Did that.
I think I
This one's
want
probably
to
front and back.
Yeah, I know.
So we do like for you guys. Other one doesn't print those ones.
8 o'clock.
I have no. No, when you print off the number and everything.
He should give to us. He never tells us what he needs. Make Lisa do it.
Yes. But I would also say it doesn't necessarily need to be open book.
Yeah. Like, our chemistry teacher they're actually gonna be.
Okay, we're ready to go. I'm showing that Kyle and Rezo were still out here right now, so we're gonna go get started. First thing up, any quick questions on section 1.2 homework. I heard from the folks here at ICC that the last 3 problems, 55, 59, and 63, all seem some difficulties. So we can look at 1 or 2 of those. Are there, anyone else feel pretty good about everything else? Davidson, are you pretty good with the rest of that? We'll take that as a yes. 55, let's take a look at 55. Before we do 55, we need to review on turn to page 94, look at the definitions that we need to employ for this problem. On page 94, it says, the limit x approaches c of f of x is equal to infinity means that for all values m greater than 0, there exists delta greater than 0 such that if x is in the interval, punctured interval without c, then f of x, an element of the interval, m to infinity. So the idea is if we have an infinite limit, that's going to go to the left. So if we have a infinite limit the idea is that the function is somehow going up to infinity as you get close to a number c. And apparently it's getting close from both sides, so likely there's an asymptote there of some sort. But it's going up to infinity from both directions. And so the idea is, unlike before where we had a horizontal bar of height epsilon and then a vertical bar of width delta, we now have a vertical bar of width delta, whatever is needed. So this is your delta here. And whatever width is needed in order to get above, and they prescribe some value m, so this is m here, and we're saying no matter how big m I make, if I make m 100 million, I can find a small enough interval of delta so that my y values get above that m. That's the whole idea that no matter how big you make your m. So unlike epsilon, the idea with epsilon is no matter how small the epsilon is, I can get within that window. But now, with going to infinity, it's not small we're worried about, it's big we're worried about. So no matter how big I make my m value, 100 million, I can get my delta small enough to get above that bar. That's the idea. Are we with us there? That's the first definition. The second definition should say something like, well, I'll just read it real quick. It says the limit at infinity. So x is going to infinity. So it says the limit of f of x as x goes to infinity is equal to L means all epsilon greater than 0 for existing n greater than 0 such that if x is a member of the interval from n to infinity, then f of x is in the interval the epsilon. So the idea of the picture there, so again, this picture goes with limit x goes to c of f of x equals infinity. So that's this picture. Now we're going to do limit x goes to infinity of f of x equals L. So a different picture. We're now, instead of getting close to a particular c value, we're getting out to infinity, but the y values are getting close to a particular value called L. So a picture like for that might be that damped sine wave we saw yesterday, or whatever else, any kind of like a horizontal asymptote. So you might have some kind of horizontal asymptote, and your graph, as you go out towards infinity, graph is getting closer and closer to that horizontal asymptote. So this number here is L, and we're getting close to it. It says that there's no matter how tight of an epsilon window I make, so if I say this is my epsilon window, this is my epsilon window, no matter how tight I make that epsilon window, I can find a value n along the x-axis. So here's my value n, so that as long as I'm past n, as long as I get past n, then all of the values, the y values, will map inside that epsilon window. So I just got to get far enough out the x-axis to get them inside that epsilon window. That's different than this one, but they're kind of similar. Both have this bar. I got to get past the bar. Here I've got to get past the bar going up. Here I got to get past the bar going right to get it trapped in the correct window. Are we clear on that? A little bit better now? Now, the third definition is a combination of both of those. If you're going to do the limit x goes, if you're going to do the limit x goes to infinity of f of x goes to infinity, the third definition puts infinities in both places, infinities for x and infinity for y. Then you're going to have both an m involved and an n involved. Notice when we've got a c value, you've got an m involved for your infinity in the y direction. When you have an infinity for x and an L in the y direction, then you have an n in your x direction. If you've got both infinities going on, you're going to have both an m and an n. Okay, with that in mind, we can now do a problem. Like 55 says, we want to this one. Use graph and algorithm to approximate the largest delta or the smallest n that corresponds to the given value of epsilon or n, according to the appropriate definition. So we're trying to show limit x approaches 1 from the right of x squared minus 1 is infinity, n equals 1,000, find the largest delta greater than 0. 1 over x squared minus 1. So middle board now. And then x approaches, was it 1 from the right? Is that what it was? 1 over x squared minus 1 equals infinity. And we have m equals 1,000. And we want to find maximum delta that satisfies the definitions. So what does the definition say? Once again, my picture. Which way am I going? My infinity is on the y direction. So that means I've got to be able to trap this function above some bar. Imagine a super high jump, and I got to be able to trap the function above that bar somehow. So whatever this picture looks like, 1 over x squared minus 1. So visually, I guess it has an asymptote at 1, negative 1, and whatever else it does in there, I don't know. But it says coming from the right, it's going to infinity. So apparently from the right, it looks something like this. In between, I don't really care because I don't care what's on the left side of this problem. There's my picture on the right. So there's my 1. There's going to infinity in the y direction. So what they're telling me is I need to trap off an m at 1,000. So I gotta put an m up here. M equals 1,000. Now you need to determine a delta. So delta is going to be like right in there. So some little distance. That's my delta distance. So that everything in that little interval, that's not really tight enough, but the idea. Everything in that little interval is above 1,000. Y'all with me?
Yeah.
Davidson, does that make sense to you?
Yes.
Come on, yeah. Okay, my picture's not very good. I want my red to intersect my green right at the black line, so I'm going to change my black line just to make it look better. So I'm going to make my black line not quite get so close to the right to there. A little bit. Anyways, so the idea is just like yesterday, I want to find effectively that intersection point. If I can find that intersection point between the black line and the red line and the green line, I've got it. Well, what's key to that? I want to get above the green line, which is 1,000, with my black line, right? I need to know which x value that makes it happen. So how did we do that yesterday? What did we do to figure that out yesterday? Did some algebra. What's going to be my algebra here? Yes, we're going to set f of x equal 1,000. We want f of x to be above that, the y value to be above that bar. So we're going to figure out what it takes to get to the bar, and then we'll say it's over meeting that, we're there. Okay, so that means I got 1 over x squared minus 1 equals 1,000. But how did we do it yesterday? We did it a little different, didn't we? We put a delta in there, so I'm going to back up just. That's the idea of orange. We want to know this point right here so we can figure out what delta is. So I'm going to back up and say what we did yesterday was we said f of 1 plus delta. 1 plus delta. Remember doing that yesterday? Okay, so there's that x value is the red line. I want that to be my x value. And that involves delta, and that will allow me to calculate delta. So this gives me 1 over 1 plus delta squared minus 1 equals 1,000. From there, it's simple algebra to solve for delta. Are we clear on that? It's the same game. The only difference is I don't have an epsilon because I'm not trying to narrow it down to a small region. I have an m that says, here's this high jump I got to get over. How do you solve that equation for delta? Self. Suggestion? Here's my first suggestion.
You're talking about like the
1 plus delta squared minus 1 equals 1 over 1,000. You don't have to do the whole problem. We'll do 59. 59 has both infinities in it. Gosh, you gotta be kidding. Limit x goes to infinity of natural log of x equals infinity. Oh. Limit x goes to infinity of natural log x equals infinity. So graphically, just first quick glance at graphically, natural log of x has vertical asymptote at x equals 0. Crosses the x-axis, and then it drifts up. It doesn't keep going. The rate of change drops off, but it keeps going up forever. And so they're saying that, what did they give me an m value of what? What was their m? 100. So they're saying we want to get above, we're going to call that m equals 100. In order to say, in this situation, in order to say we're close enough to a infinity, all we got to do is get above the bar of 100. That's not very big, but really good enough for this problem. And then in order to show that, we've got to show that we only have to get past a certain point in the x-axis. We'll call that n. So as long as the whole idea is, in order to be above that bar, I've got to be to the right of n.
Mm-hmm.
Okay, so what do you think? How are we going to crosshairs on that you're aiming at now? What's the name again?
You want to do it algebraically again?
Good. Excellent. And what am I going to write down as my algebra? I had a starting algebraic equation right here, which I then solved. So I need a starting algebraic equation right here. What should I write as my starting algebraic equation?
Natural log of x.
Equals.
100.
Yeah. And I assume that x is going to be.
That's almost right. That's almost right. It's an excellent, good idea. And back to here, we used the function of 1 plus delta because that was my demarcation that I was looking where I wanted to find that demarcation point. What's my demarcation point here?
Good.
Yeah. So instead of x, I'm going to just put n there. There.
If it's not, it's 100.
Thank you. It should be 100, not 1,000.
You do this. You divide out the natural log.
Natural log of n equals 100. I'm trying to figure out what my n value is so that the natural log of it gets above 100. That's the whole objective. So how do I figure that? N equals e to the 100.
Go.
Give me a decimal approximation for that. Be careful, your calculator might bite you if you try.
Yeah. It's putting it in scientific notation.
Yeah.
I can't dig it. It's like 40, 30.
0.68 times 10 to the what?
43rd power.
It's-
Oh my gosh.
It's even bigger than our U.S. national debt. I mean, that's huge.
I think it's based on Euler.
Are we with us there? So we're saying as long as x values, any x, so let's summarize this. What this says is if x is an element of the interval e to the 100 to infinity, so if I have any x value in that interval, then f of x, which happens to be natural log of x, will be an element of the interval 100 to infinity.
Yeah.
And it ought to be clear that I can, for any m value you name me any m value, whatever you want, you can make it 1,000 if you want it, I can now calculate an x value interval that will force, so any x in this interval will force f of x to be in that interval. No matter how high I make that bar, I can get above it by doing the same thing. Same idea here. Going back to this one, to summarize this one, we would say, so if x is an element of the interval, what did we have here? 0.0005, so 1 to 1.0005. So if x is in this little tiny interval right there, from 1 to 1.05, then my f of x values will be high enough to reach the bar of 1,000. So they'll be in the interval from 1,000 to infinity. And again, the idea is no matter how big of an m you make, I can go through this game and figure out a small enough interval to make sure my outputs land in that interval. Does that make more sense now? So it's kind of similar to the other problems. Again, the other problems had two constrained windows, horizontally and vertically. This game has one constrained vertical window, but it's open up above, and this one, it's open both directions. You're still trying to get in the whole idea is to try to get in a specific region of the graph. However that works. The algebraic to do it is it's just a matter of setting your function equal to that special point you're concerned about and figuring it out. Y'all, does that make more sense now on those problems?
Yes.
Okay, good. What's up next then?
What's up?
Section 1.3. Okay, first of all, let me just make a quick announcement. If you haven't looked at Moodle recently, I did post finally some homework for section 1.2, and once we've got that and worked on it, I also went ahead and posted the homework for 1.3. We're going to cover right now. And on Tuesday, coming up this next Tuesday, we have a test on called Block 2, which is sections 1.1, 1.2, and 1.3. So there's 3 sections. So we only have one more section to cover, and that's what I'm calling, the book called section 2 of the formal definition, and then they call section 3 epsilon delta proofs. And so that's what we're going to do in the next section of proofs. Rather than this is kind of not really a proof, it's more trial and error almost with a little bit of algebra. Proofs are a little more formal, a bit more formal. And that's what's in section 3. So we need to start on section 3. So I'm going to start by, I handed out, and this cleaner handed out to your class over there, this third part. There's not a whole lot of to do. It's mostly reading and then examples. There's only one little reading at the top, and so I'm going to start by writing that on the board. I'm going to go over to the left side here and talk about the definition from this formal, very formal standpoint and how it relates to what we've been doing. Okay. So it says in a formal definition that the limit of f of x as x approaches, did I write A or C? Okay. So it'll match what's on that sheet, which is different than the book. The book gives a C, whatever, A. Equals the number L means, and now here's the formal, layout. You'll see words like we studied back in the chapter 0. For all epsilon greater than 0. This is right on the top of the sheet there. There exists delta greater than 0. That's that. If 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. That's a very much more concise way of giving a definition of a limit than what we've been saying in the past. Very concise. Now let's make sure we're clear on different pieces of it and analyze it, and then we'll do some examples. So the first thing is, I don't know if blue really shows up very well as distinct from black, but we'll try it. First of all, does everyone recognize the idea of an if-then here? So here's your then, that's your then, and that's your conclusion. This is your conclusion. And everything else is the hypothesis. So all of this is the hypothesis. Everyone recognize that? We studied this in section chapter 0, talking about the hypothesis and the conclusion. Good. That's important to recognize. So how did we do when we did a simple proof or two back in chapter 0? How did we do that? We started by let the hypothesis be true, and then showed that the conclusion had to follow. Well, that's the same game here. We're gonna set up all of this hypothesis stuff, and then we're gonna use some algebra and some trickery and stuff, and we're gonna come up with the conclusion at the end. That's the overall picture of the game. Now, within the hypothesis, let's look at the pieces of that. I'm coming right back. So, for all epsilon greater than 0, do you recognize this for all business right here? What does that mean?
You have to find one to prove it wrong.
Not have to find one. Every single possible epsilon greater than 0 has to work. Epsilon can be 10, epsilon can be 2.1, epsilon can be 0.00000001. Any possible epsilon you can imagine has to work. That's what that says. And that's from, again, chapter 0. Then we see these words. There exists delta greater than 0. Now remember what that means. You only need one. You can have more than one, but you only need one. Now I would reference back, let's compare back over here. Epsilon and delta, like here. Is this the only delta that will satisfy this problem? We found delta is 0.005. Is that the only delta? No, that was the maximum delta. If I took a delta smaller than that, it would get me above the bar. Agreed? So there exists delta, doesn't require all of them, but it does require at least one. We have to be able to find that one. Okay? And the rest of it says if. So if 0 is less than absolute value of x minus a is less than delta, we clear what that means. So you write absolute value of x minus a in algebra. What did that mean in algebra? How did you interpret it? It was the distance between x and a. Y'all remember this? On a number line, I have numbers a and b. How do you determine the distance between those two numbers? You take the absolute value of the difference, right? So this is what you did in pre-calculus algebra. Absolute value of a minus b equals the distance between. That's pretty example. So I have absolute value of x minus a. A is the middle point of my interval. So I've got this graph. I'm thinking of a graph. Like before, we've got some function going on here. Here's my number a, and I'm looking at x values. So I'm looking at an interval of x values so that the distance between, and these are my x values. All of these in here are x values. X, and these are x. So any x value in that interval has to be, the distance has to be greater than 0, but less than delta. So think about that. If I pick an x value, if this distance out to here, out to that endpoint right there, this distance, if this is a plus delta there, like we've done before, this is a minus delta, like we've done before, do you recognize that the distance of any x value in that interval from A to any x value in the interval, the distance is going to be less than delta. Because delta is the distance from A to the interval. So if I pick any x in there, the distance between that x and that middle point, that distance, is less than delta. That's what this is. What about the other side of the inequality? It says the distance from any x in here to the middle A point is greater than 0. What is that? It can't be on the A. The only way that the distance between these two numbers can be 0 is if x is equal to A. But we've always not wanted x to be equal to A. We've kept it off of the A, right? So this statement up here that we have 0 less than delta. That statement is equivalent to what we've seen before, that x is a member of the punctured interval A minus delta to A union A plus delta. So all that little concise notation with absolute value says the same thing as what we've been saying, but just in a more concise fashion. Similarly, the absolute value of f of x minus L is less than epsilon. You see that that's saying the same thing? That our distance between f of x, when you've got this epsilon window, the output y value that we're talking about related to a particular x value, the distance between that output y value and this special number L, that's the limit, that distance is always smaller than epsilon, which means it's in that epsilon window. So these two statements here are just a more concise way of saying what we've been saying. Nothing new there. That's just an understanding of the statement of that definition, the formal definition. It's just a more concise way of writing what we've been writing. I'm going to start on the middle board here. We're going to do an example now. So instead of doing the example that's on the page, because you can read that example yourself at home, I'm going to do a different example. Okay, let me make up an example for you. Prove that the limit x approaches -1 of
I can't even see it.
2 minus 3x
That's great.
equals, what is that, 5?
Nice.
So before I start the formal proof, I'm going to just talk graphically for a minute, like we've been doing. So the idea of this is that some function graph that's 2 minus 3x. So it's 1, 2, and it's got a steep slope, so it's going like this. And we're saying that this is the number 1 right here, -1 right there. So if we get close, if we say that we want to be within a certain distance of 5, so this is going to be up here, it's going to be 5, say. So we want to be in some small interval around 5. So this is my, we'll call this my epsilon window. We need to be epsilon above and below 5. And we have to be real close to -1 as well. And so we'll call that my delta window. Well, the ideal, again, is by that definition, in order to have the distance from 5 to any y value on the black line, in order to have those y values land in the red window, I have to have x values in the green window. Well, we've got to prove that. That's just a review of what we've already done. Let's prove that with this formal definition. So the way we start is, for any kind of proof, we let the hypothesis happen. So let's let epsilon be greater than 0. Because, again, what did we say about the for all epsilon greater than 0? What has to happen for all epsilon greater than 0? It has to be true for any possible epsilon. So you're not going to specify epsilon. You're not going to say, let epsilon be 7, or let epsilon be, you don't get to. Now, on some problems we've done, you were given an epsilon equals 0.01, and you had to find a delta. But that was just a specific case. That doesn't prove. To prove, you have to do it for any possible epsilon. So I'm not going to specify epsilon. I'm just letting it be any number that's positive. But then what did we say about there exists delta? What did we just discuss about that? What's that?
Yeah. Is that supposed to be epsilon or delta on the board?
That's supposed to be epsilon. Let me rewrite that for you, so let's look at it.
Okay, thank you.
Okay? So with the delta part of the game, there exists delta, and there has to be, Justin said, at least 1. And because it's an existential, we have to identify the 1, or at least 1. So we get to pick it. So I may not know right away what I want for my delta, but here's that in the process, it comes next. So I'm going to say choose, because I get to pick it. There's one of them, I got to find one, and I'm going to choose delta, but I don't know what it is just yet. So for right now, folks, I'm putting in a dotted box on my proof, so I remember to come back and fill that in. So I don't know what really goes there yet. I'm not sure what number I want to put in there. But I get to choose it because I just have to demonstrate that I can find 1. Because it says there has to be 1 at least. So I have to demonstrate that I can find it. Okay? And then there's still more. That's two statements out of the hypothesis. The next part of the hypothesis is that x values have to be in this interval. This is defining an interval so the distance is appropriate and fits in the delta window. So I'm going to assume that's true. So assume x is located so that 0 is less than the absolute value of x minus, and my a value is -1, is less than delta. So I have now, in what I've written on the board so far, all I've done is set up the proof by getting the hypothesis all assumed to be true. I set them up. Now I've got to show through some algebra that the conclusion, this part right here, has to follow from this information. Are you with me? That's what we're trying to set up. Now, first of all, I know that's an x plus 1 because minus a negative. So that's fine. But what do I do? I mean, I'm trying to get this statement. Let's go here. I'm just thinking on the side. So on the side, this is some scratch. So we're given that 0 is less than absolute value of x plus 1 is less than delta. That's what's given right there. And we want the conclusion. The conclusion is the absolute value of f of x minus L. Well, f of x is 2 minus 3x, and then minus L. L is 5 here. We want that to be less than epsilon.
I mean, I know what he's writing.
Yeah.
I'd like to see.
I'm just kind of making notes and some scratch work so I can finish my proof. I don't do all my scribbling in my proof. The book does nice, very simple proofs. They don't show you all the thinking and all the scratch work that goes into it. They just give you this nice little formal final answer, and that's what we're going to do. I got my start of my formal answer, and now I'm going to do some scratch work, and then I'm going to go back and finish my formal answer. Okay, so given this little bit of information, I have to somehow get to that. Meaning, there's got to be a relationship between delta and epsilon. That was the whole key. Remember when you were doing it with the graph? We gave you an epsilon, and you had to use your graph or use algebra to find a related delta. You had to find a related delta. Well, the thing is, instead of doing it for a particular epsilon, now we want to find the relationship between delta and epsilon in general. Understand? Before I gave you a specific epsilon, and you found a specific delta that went with it. Okay. Now, I'm giving you an unspecified epsilon. You want to find the related delta, so it has to be a generic type of relationship. That's what we're looking for here. Well, I'm going to think for a minute out loud. I'm going to say, well, you know, what do I see going on right here? That looks kind of confusing and messy to me. So I'm going to clean this up a little bit. So what does this simplify to here? Well, 2 minus 3x minus 5, what does that give me? That gives me like a negative 3x. Did I do that right? That's 3x. And minus 3 less than epsilon. Y'all with me here?
Yeah.
Just cleaned up my algebra a little bit. Now, I observed one more thing. Like, again, I'm thinking ahead. I want to find a relationship between epsilon and delta. Those are the things I'm looking to match up somehow. Delta is related to x plus 1. Anybody see an x plus 1 in here hiding out? Some people are going, yeah, I see it. Others are going, what are you talking about? There's no x plus 1 there. I see an x plus 1 there.
Yeah, I get
So,
it.
But if we factored out a negative 3,
That's nice.
you see now I have an x plus 1.
Mm-hmm.
That's good. We just need to clean this up a little bit more. So there's a property that says if you have a product inside an absolute value, you can have the product of two absolute values.
Oh, this needle. Hang on a second. I see what he's doing.
So far, so good? What's the absolute value of negative 3?
3.
Good.
Yeah?
Right? So 3 times absolute value of x plus 1 is less than epsilon. I'm getting real close here, folks.
I'm so close. I'm so close, bro.
I have up here that x plus 1 is less than delta. What if I divided this by 3? What would I get?
What would you get? That's a fair question. It's like a mirror. Oh my gosh.
Absolute value of x plus 1 is less than absolute value of x plus 1 is less than epsilon over 3. We all follow that, and that's just simple algebra.
Mm-hmm.
There's your tie, folks. Do you see the tie?
No, but keep on going.
X plus 1 is less than epsilon over 3. X plus 1 is less than delta.
I don't buy it.
Maybe delta could be epsilon over 3.
Sure.
You see that this and this look pretty much the same thing? So this tells me right here, these two statements, I need delta to be equal to epsilon over 3. Now think about it. Let's stop. Well, I'm going to finish the proof in there, I promise. But think about back when we were doing the graphing calculator business. I gave you a fixed epsilon, and you found a fixed delta. That delta was somehow related to the steepness of the graph. Didn't we talk about that? How the steep of the graph, it changed how big delta had to be? Don't we talk about that? Well, that makes sense to me then, that given any epsilon, the delta has to somehow be related to that epsilon. And I found it right there. Here we go. Back in my proof, in my little dotted box, I'm going to put the delta is equal to epsilon over 3. Or so good? We're not done. We still have to show the conclusion. We have to show that. Well, that's going to give it to us.
Okay.
This is us. Now we just basically replicate what I just did. Now, my scratch work now basically kind of becomes part of my proof. This gives us, and I'm going to show this statement. I'm going to start with that left-hand part and show that it's less epsilon. This gives us absolute value of f of x, which is 2 minus 3x, minus the limit 5. Now, I'm not going to say it's less than epsilon. I'm trying to show it's less than epsilon. I want to show it. So what is this equal to? Well, we just showed over here this is equal to the absolute value of -3 times x plus 1, which is equal to, and I'm skipping a couple steps there, because the absolute value -3 is just a 3, I'm going to say that this is 3 times the absolute value of x plus 1. Y'all with me? I'm replicating my algebra. I'm skipping a couple of steps in there because I can see that. I can see if I factor -3 out, then absolute value -3 is a positive 3. But now, what do I know about x plus 1 that's given in this, not over there, and what I've already stated right here in the proof, formal proof? What do I know about x plus 1 that's already stated right here? It says x plus 1 is less than delta. Agree with that? So this says I've got an x plus 1, so I can say that this is less than 3 times delta.
Where did the 3 come from?
Pretty clear.
We're already.
I know that x plus 1 is less than delta. Agreed? So if I have 3 times x plus 1, wouldn't you say that that's less than 3 times delta then? That's all I've said. 3 times x plus 1 absolute value is less than 3 times delta.
Okay.
But what did we just say about delta right here? Epsilon over 3. So equals 3 times epsilon over 3. Uh-oh, what happens with those 3's? Cancel out and I just get epsilon.
Nice.
Thus, whenever 0 is less than absolute value of x minus -1 is less than delta, then absolute value of 2 minus 3x minus 5 is less than epsilon. And we've shown it. We have shown that given any epsilon, it doesn't matter what epsilon you want to name, I can find a related delta so that I can guarantee that any x value in this little delta interval, will have a y value that matches in the epsilon interval. You can now name any epsilon you want and I'll find you a delta. That's what that proof does. Since it's for any epsilon, not a specific one, then it has proven the limit in general. Okay? That's how you do a home proof. We should do one more and let you try it yourself. Let me just make up one more and let you have a few minutes to try it yourself. I'm going to go over here to the whiteboard. We got one. Let's go over to the whiteboard. Let's do another simple one. The minute x approaches 2 of whatever, 5x minus 3 equals 7. But right now, on your notes paper, try to replicate what we just did. So meaning, you'll want a formal proof answer, and any kind of scratch work you do is not written in the middle of your proof. It's off to the side somewhere. Clear on that? Formal proof needs to look very clean and neat. The scratch work needs to be off to the side and kind of indicate. You can draw a picture if you want, but you don't have to. You can entirely do this without drawing a picture. If you want to draw a picture, great, do it, please. Give you a couple minutes on that. See what you can get done. Gray's will finally get here.
I've been here.
Oh, you're sort of, yeah. Amanda, can you pan back just a little bit, make it a little wider angle? Because we're not really getting Grazo or much of Sammy.
So long.
Is that good?
That's good, thank you.
Dang it. Thomas Jefferson right now.
I'm just not lying on that. We'll meet up in a minute. I'll copy my notes. Okay, we need to quickly go over this and try another problem. That's a little more complicated. I have written out a proof here. Hopefully you got at least most of it in the time you had. With a little practice, you'll be able to do it faster. So in review again, the proof starts with setting up the hypothesis. So I've got to have any epsilon that's greater than 0, so I don't get to pick it. I do choose my delta because I just have to show that there's one, and I choose a specific delta that's not an actual number, but it's related to the epsilon. This time it's going to be epsilon over 5. And we also assume that we've got x is located in that delta window that we just specified the delta. So now we're trapping our x values right here. We're trapping x values close enough to number 2 by this delta, and then we're showing that the f of x values, the y values, get close to the number 7. That's what we're trying to show. So we've got our x values trapped this close to the number 2. We want the y values to be trapped epsilon close to 7, and that's what happens. The distance from y value of 7 and this f of x value is shown through a little bit of algebra that we have right here, a less than symbol that appears because of this assumption. We've related x minus 2 to delta, and then because delta is directly related to epsilon, then we can change to epsilon in our statement, and then it simplifies to epsilon. So we've shown that this absolute value is less than that epsilon, and that's what we just summarized down here at the end. Questions on that? We follow that? Okay, so another type of proof that we need to handle is quadratic, and we have an example on the handout there I gave you, and then there's examples in the book as well. But let's look at one real quickly and try to, I may not get the whole proof done, but we'll get as much as we can done. Just to make sure, just to go quicker instead of making something up, I'm going to take the one right on here. Okay, so limit x approaches 1 of x squared plus 5x minus 3 is equal to. Okay, so one more time, we're going to set up, the proof starts off similar, but the difficulty is that being quadratic causes a curve instead of a straight line. So figuring out what delta is not as easy as we discussed yesterday. When you have linear, then delta left and delta right are the same delta, and it doesn't matter. But when it's curving, one side's going to be bigger or smaller than the other. So this gets a little more complicated. So we're going to try to get through it. So my proof. We're going to start off the same. Let epsilon be any number bigger than 0. I'm not going to specify my epsilon. I'm going to pick a delta. I don't know what it is yet, so I'm going to leave it blank. And come back to it in just a minute. We will assume, once again, the start is always the same. Assume that x is located such that 0 is less than absolute value of x minus 1 is less than delta. And then this gives, what does this give us? Now we want to show that, and I'm going to start it off, I'm not going to finish it yet, but we want to show that the distance from the function to the limit value is smaller than epsilon. So we want to show that the absolute value of this function, x squared plus 5x minus 3, minus the limit value. That distance between those two numbers, the limit value and the y value from the function, that distance between those two y values is smaller than epsilon. That's what we want to get to, but we're not there yet. We're going to work. Okay, so I'm gonna do a little scratch work in the same type of game as I did over here. This is going to be a little bit tougher because I got quadratic. So, again, I'm given that 0 is less than absolute value of x minus 1 is less than delta. That's what's given. I want to get to the absolute value of x squared plus 5x minus 3 is less than epsilon. So kind of in the same game as I went through over there, I'm going to start fiddling with what I want and see if I can somehow tie it back to what I'm given. This is the easy part. So what I want, so I'll change colors just to keep it like I did before. Already. So what I want is absolute value of x squared plus 5x minus 6 to be less than epsilon. And then that, I got a lot of algebra. I could probably factor that. That looks like it probably factors as, what, x plus 6 times x minus 1? Y'all agree with that? Y'all with me there so far? Then I have a product of two factors, x plus 6 and x minus 1. Well, x minus 1 looks a lot like that x minus 1 right there. So I'm going to split my absolute value up into absolute value of x plus 6 times absolute value of x minus 1. Now, here's the problem, folks. Previously, when I got to this stage, I had some multiplier here on the side, a constant multiplier like 3 or 5 or something. And I could directly now tie delta to epsilon through that constant. But now my multiplier is not a constant. It has a variable in it. There's my complication. And here's the game that we play to fix that. Let me get it up in color. So to handle this one is easy, because this one is tied to that one. That's obvious. But this one is a question mark. How do I get there? Well, since delta, the thinking goes this way. Since delta is going to be some small number, then certainly it's going to be less than 1. So we'll just start with, let's let delta be less than 1. It's got to be less than 1. So if delta is less than 1, and x minus 1 absolute value is less than delta, then this means that I've got absolute value of x minus 1 less than 1. We follow that. So right here we've got absolute value of x minus 1 is less than delta. Here I've got delta is less than 1. You put those two statements together and you can get that statement. What does this statement mean from algebra? Right here, this absolute value of x minus 1 is less than 1. So what does that mean in algebra? And 1 is less than x minus 1 is less than 1. Over that. If the distance is less than 1, then it can be to the right 1 or to the left 1. That's from algebra. Anyways, keep going. That's algebra. Now, I want my objective is to handle x plus 6. So to get an x plus 6, I'm going to add 7 to that to get an x plus 6. So if I add a 7 to everything, I get 6 is less than x plus 6 less than 8. And we know that negative 8 is certainly smaller than 6. So this negative 8 is certainly smaller than 6. That's no problem. So between negative 8 and x plus 6 and 8, I can go reverse and get absolute value of x plus 6 is less than 8. So again, by pre-calculus, if you have a negative of a number and a positive number with something in between, then you can say the absolute value is smaller than the positive, back up here. So I now have, by making this little statement, I now have absolute value of x plus 6 is less than 8. That gives me everything I need to know to do delta. So let me show you real quick. Delta is going to be not a single value like we did over there. It's going to be a statement about the minimum. It's going to be the minimum of either the 1 that we picked right here, or, and then we're going to use epsilon divided by 8. Epsilon divided by 8. So like over there where we had that constant multiplier, 3 or 5, now we're saying that x plus 6 can be trapped by the number 8. So I can replace this thing, I can replace x plus 6 with an 8. That's like having a 3 or 5. So now we can continue. Let's finish the process real quick. So this factors as absolute value of x squared plus 5x minus 6, which factors as absolute value of x plus 6 times absolute value of x plus 1 to x minus 1 part. And what does that mean? Well,
It's less than something.
this is less than okay, what did we say about the x plus 6? X plus 6 is absolute value of x plus 6 is less than 8, right? That's what you said. We can put an 8 to the x plus 6. And x minus 1, right here, x minus 1 is less than delta, so we can put a delta right there.
Great.
But delta is also smaller than, is equal to, no worse than epsilon over 8. So I can replace my delta with an epsilon over 8. So this is less than 8 times epsilon over 8. It says the minimum, so at worst, it's got to be the smallest of the two. So at worst, it's epsilon over 8. And so now you get epsilon. So we've shown it. There's one last statement. I know we're out of time. You say the best, whatever. But the point is with quadratic, it's a little more complicated because you have 2 factors. So one factor goes directly with the delta. The x minus 1 goes directly with the delta. And the other factor has to have a little special work on it. There's some notes on that handout I gave you. There's notes in the book on that. So you have a homework for section 1.3. There's not really anything to do on the handout. Well, actually, there's 3 problems. So practice on there, plus some homework problems. Monday will be to wrap up and get any homework questions covered, and then any last-minute questions before the test on Tuesday. So, again, you need to try some of these homework problems because if you don't know, I'm not planning to collect it, but if you don't have tried it, you don't know what you don't know. All right, see you on Monday. Have a good weekend. Be safe out there.
Is it gonna be
Don't
a?
forget math club tomorrow.
Is it gonna be a group test again?
Carson.
What time is that?
No, this will not be a group test again. This will be an individual test. You will be allowed to use your calculator. Will be allowed to use your calculator, but it will be an individual test. So this will be a more standard, traditional test.
You can have it for the rest of the 30 minutes. I have to leave.
I know that.
I got stuff for you to do.
All this like that.
What time does it end? 11.
And where's it gonna be?
So what's that?
The traffic was funny at first, but now it's just annoying. I left like 15 minutes earlier than I normally do, but I got caught behind a vehicle.
Do you live near Farmington Road? Is that the problem?
No.
Oh.
No.
Oh. I
He
got.
lives 10 minutes from me, and I left the house like 15 minutes early, and I got here like the third
I left the
person.
house 15 minutes early, but I got stuck behind a car that was going anywhere from 10 to 15 miles below the speed limit.
Why can't you?
There was a wreck in front
Why
of me.
can't you have better luck?
I just get terrible luck, and after
then the girl that
after
got
that
out
car
was
was out of the
speeding.
way, I was behind a bus, and
Well,
then I
I-
got caught behind another bus.
And it was just
So
No,
on
I take it back.
like October 11th or 12th, we're on our
Do you
junior
wanna come
field
with me
trip.
when I
And
need to submit my?
Edison Thermal is scheduled to have class, but DCCC is not. Like for the whole fall
Yeah,
break.
did we not have fall break? I was looking at the class schedule.
Different time.
So we really don't have a full fall break.
We have a partial fall.
October
We have
11th
two
and
partials.
12th.
I think so. Those are the ones that I know about
Are you
because
sure about that? That's the senior trip?
junior.
Have to do the diploma.
You're junior?
Yeah, I know.
So it's just you
It's only
and
two
me,
classes.
Josh and Dylan and
What if we don't have a last
Well, even in the 10 minutes, even in the 10 minutes before class, it's still good.
Is the college not closed?
It's just 2 paragraphs.
No, I gotta work.
Oh,
I'm sorry. I only have off the last.
So you're reading through the lab?
You don't have a fall break?
no.
Oh, because
I
of
mean,
this
I think I
class.
have the last 2 days off, Thursday, Friday.
Is it like a teacher that's doing it?
I know.
So
Oh,
But we'll
we
figure it
will
out.
have this class, right?
But I don't know.
I thought our fall breaks matched.
Not according to their online.
Well, on their online thing, they don't even have fall break like listed
It's
anywhere.
called like PD.
Yeah, but that's only like 2 days.
That's
like,
only
it's
for
not-
Yeah, it's-
teachers. That's not for students.
I don't know. I was just looking at the.
Yeah, like I feel like
We're just confused and we wanted
because the
to.
the class
I
schedule.
have a printout of the calendars somewhere, and I'll figure it out.
All right.
Go to school.
Can you also ask him if he'll post the answers to those worksheets so we know if we did them?
Why don't you email him and say that?
Because it's easier for you to ask.
No,
He doesn't like me, Miss Klinger.
He does.
You don't know that. You're just saying that. to make
Just
me feel
ask
better.
him. I'm sure he will do that.
I never really know what's going on. I just kind of write down what he
Well, ask
thinks
questions after class.
and pretend that
I
I did
pretty
them.
much know what's going on. I mean, I'm working on other stuff at the same time, but I have an idea of what's going on. You can do it.